Now, CLT, central limit theorem, the key concept. The central limit theorem allows us to use a normal distribution for some very meaningful and important applications. The bottom line is we use this for application.
A sampling distribution of sample means is a distribution obtained by using the means computed from random samples of a specific size taken from a population. Sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population.
It's important to understand the sampling distribution has been already discussed previously in the previous section. And for example, when we say sampling distribution of a sample means, that means you have a sample size, a specific sample size, and you calculate the mean. And you continue with the next one and the next one. And if you set up the sampling distribution of that, is known as a sampling distribution of sample means. And when we do that, it may create some sort of an error. The error is due to the fact that we are dealing with a sample, not a population, obviously. Now, here's the conclusion. The distribution of sample X bar will, as the sample size increases, approach a normal distribution. In other words, as n gets larger, the distribution becomes more and more normal. And so in that case, the mean of the sample means mu of X bar equals to mu. Sigma of X bar is sigma over square root of n. So you have a bunch of means. Remember that. I want to make sure you understand what this means. This means we have x1 bar, x2 bar, x3 bar, x sub n bar. I want to make sure we understand what's happening. So we have the first group. The first group, we take the average, the mean, it's x1 bar. The second group, their mean is x2 bar, and so on and so forth. Now, this is our new data. For this new set of data, calculate the mean. We call it mu of X bar. Calculate the standard deviation. We call it sigma of X bar. So for all these X bars, remember X1 bar, X2 bar, and so on and so forth. All these X bars, we can calculate the mean using the formula, which is what add them up, divide by size. We can calculate sigma, or standard deviation, which is what? Summation of x minus x bar over n minus 1. Calculate that, and because we have one sigma, actually summation of x minus mu, quantity squared over capital N. This doesn't change, it's the same as mu. This one, it's sigma over square root. It is smaller by that much. This is called the CLT, central limit theorem, and we use that to solve applications. So let's go to the next page. So this is the synopsis of the section. Understanding the concept is extremely important. Central limit theorem and the sampling distribution X bar.
A sampling distribution of sample means is a distribution obtained by using the means computed from random samples of a specific size taken from a population. Sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. The central limit theorem tells us that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. 1. The random variable x has a distribution which may or may not be normal with mean mu and standard deviation sigma. 2. The simple random sizes of all samples of all size n are selected from the population. The samples are selected so that all possible samples of the same size n have the same chance of being selected.
Conclusion.
The distribution of sample, can you repeat the name? Sorry.
Sample X bar.
Okay, well, as the sample size increase approach a normal distribution, the mean of the sample means is the population mean. I'm sorry, it's really blurry. I can't really see it.
So mu of X bar equals mu. Go ahead.
Okay, the standard deviation of all sample means, also called the standard error of the mean, is
Sigma of x bar equals sigma over square root of n. Go ahead, please.
okay. For the sample size, I see that
N
it's n.
larger than 30.
Okay, the distribution of the sample mean that means can be approximated reasonably well by a normal distribution, for the approximation becomes closer to a normal distribution as the sample size n becomes larger. If the original population is normally distributed, then for any sample size n, the sample means will be normally distributed, not just the values of n larger than 30.
Now, what do we mean by that? I want to give you the synopsis of what's happening here. In short, and this is extremely important to understand, is really the synopsis of the whole thing written at the bottom. What you have, either the population is normally distributed or not. If the population is normally distributed, so is the sample. But if it's not, n must be larger than 30. When we read the question, it says the population is normally distributed, and we take a sample size of anything, even smaller than 30, that's fine. We are dealing with a normal distribution. The sampling distribution of x bar is normally distributed if the population has a normal distribution, or we use n larger than 30. So I want to repeat that because I can't emphasize this enough. If we know the population is normally distributed, sampling distribution of x bar for any sample size, we consider normally distributed. End of this thing. If we don't know anything about the population, or in fact, if we do know the population is not normally distributed, then we have to pay attention to n. The larger the n, the more normally distributed the sampling distribution of x bar. How large is good enough? We want it to be 30 or larger than 30. And in those cases, mu of x bar is mu, and sigma of x bar is sigma over square root of n, and this is called CLT, the central limit theorem. Central limit theorem. All right. So z is x bar minus mu of x bar over sigma of x bar. Now the numerator is the same, x bar minus mu, makes no difference. But the denominator, sigma of x bar, is sigma over square root of n. So let's see if we can do a question and see how things go.
An elevator has a sign stating that the maximum capacity is 4,000 pounds, 27 passengers. This converts to a mean passenger weight of 148 pounds when the elevator is full. Assume a worst-case scenario of the elevator being filled with 27 adult males. Adult males have weights that are normally distributed with a mean of 189 pounds and a standard deviation of 39 pounds. A. Find the probability that one randomly selected adult male has a weight greater than 148 pounds. And B. Find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds.
The idea behind this is very simple. It goes back that in the old days, when they were designing things such as an elevator or a boat, they would pay attention to the average weight and make a decision how many passengers they could have. Now, needless to say that the average weight has been increasing, and that's why every so often things have to be re-evaluated. So when you say 27 adults, 4,000 pounds of total, on the average about 148 pounds. That would be if you can assume that. However, nowadays we are looking at a different mean. So the very first thing we do, this is a word problem. So what is given? As we read the question, it is normally distributed. Mean is 189. Standard deviation is 39 pounds. So the very first thing we do, we write the given. What is given? Mu is 189. Sigma is 39. And by the way, find the probability that one randomly selected adult, n equals 1. We are dealing with a normal distribution, so we want to find the probability that x is larger than 148. So when we want x to be larger than 148, that means look at the graph here. And by the way, as far as the graph is concerned, I'm interested in drawing the graph for the z-score. So if you don't do the graph here, that's fine. But if we want to stick with that, mu is 189 and we want x to be 148, and we shade the area to the right of it. However, the way I would do it, I would do that for the z. What do we mean by that? First thing first, z equals x minus mu over sigma. Look at the top formulas and pick the right one. Calculation results in the z of negative 1.05, and we want z to be larger than negative 1.05. Let me show the graph here, and then I'm going to erase that. So I would graph something like this. Of course, this is not to scale, and then I want z larger than negative 1.05. Even this is not to scale, so negative 1.05. Remember, this is 0. So I want this area. So this is the way I would graph it. I highly recommend you graph this. Whether you do it with the z or x is fine, but the z makes more sense as far as the graph is concerned. And I'm going to assume everybody can read from the table, and right now, or use the technology to come up with the answer. Either way makes no difference. You can use the table to read this much with the negative z-score minus 1.05, read that, and then subtract it from 1. And it gives you 0.8531. So if you pick 1%, what is the probability that his weight is larger than 148 pounds? It's about 85%, 85.31%. That's huge. And the simple reason is because the average is no longer the way it was, 140. When we look at part B, we want to find the probability that a sample of 27. Now, I want you to pay attention to number 27. Randomly selected adult males has a mean weight greater than 148 pounds. Now, over here, remember, n has to be 30 if you want to use CLT, if the population is not normally distributed. But since the population is normally distributed, we don't have to worry about that. So we are dealing with the normal distribution. Mu is 189, sigma is 39 pounds, and n is 27. So we're going to use normal distribution if the original population is normally distributed or n is larger than 30. In this case, the original one is normally distributed, and we are going to use CLT anyways, okay? Because the original population of weights of males has a normal distribution. So samples of any size will yield means that are normally distributed. Now we're going to continue with the same thoughts. I'm going to erase this. You no longer need that. And what I want you to pay attention to now, what happens to the formula? We had the probability of x is larger than 148. Take a look. This is what we had. Now we change this to probability of x bar larger than 148. Find the probability that the sample of 27 randomly selected adult males has a mean weight, and this yx bar, probability of the mean weight. Therefore, we're going to use the second formula, z equals x bar minus mu of x bar over sigma of x bar, or x bar minus mu equal x bar minus mu over sigma over square root of n. So mu of x bar is mu, sigma of x bar is sigma over square root of n, 39 over square root of 27 or 7.51. This is as far as the graph is concerned. And we end up with this situation, meaning the probability of a z larger than negative 5.46. Again, I would not graph what we see at the bottom left. I would graph this one. Again, the shape that I'm going to come up with, it's completely off and it's not important, but it helps us with the result and finding it. The idea is that this is the z, so that refers to 0. And so negative 5.46 is here, and I'm interested in finding this area. Just by looking at the graph, you see it's almost 100%. Okay, of course, you have to read it from the table or using the technology. So I would graph this. By no means this is to scale. If we want to go with the scale, notice what happens with X bar. It has a smaller variance. I want you to pay attention to sigma divided by square root of n. Sigma is 39. Sigma is 39. But sigma of X bar or sigma over square root of n is a lot less. That's why if you compare this one and this one, look how tiny the new one is. When you graph it for the sake of reading the table, it doesn't matter if it's to scale or not. All I want you to do the reading properly from the table. So with that being the case, we're going to finish the job. By the way, when you go to the table, to the left of -3, normally they use 0.0001. To the right of +3, they use the same thing. You can double check that, or 3.5. And this is not accurate, obviously. This is a rough estimate. The idea is to say when we go to the left of -3, there is not much there. To the right of +3, there is not much there. Okay, but if you use the technology, you get completely a different answer. So it's almost 100%. So here's the interpretation. There is a 0.8534 probability that an individual, just one individual, will weigh more than 148 pounds. However, there is a almost 100%, 0.999. Now you see there are a lot of nines and then 8 if you use the technology. Probability that 27 randomly selected males will have a mean weight of more than 148 pounds, given that the safe capacity of the elevator is 4,000 pounds. It is almost certain that it will be overweight if it is filled with 27 randomly selected adult males. Let's look at another example.
Assume that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit, as is commonly believed, with a standard deviation of 0.62 degrees Fahrenheit. If a sample of size n is equal to 106 is randomly selected, find the probability of getting a mean of 98.2 degrees Fahrenheit or lower.
It's important, as I mentioned, to see what is given to us when we read this question. As we read the question, use the mean, use the standard deviation. Remember, all of it refers to population. That means mu and sigma. So if a sample size of n, so n is given, is selected, what do we want to do? It doesn't mention it is normally distributed, but it doesn't have to because it is larger than 30 and therefore the CLT central limit theorem applies. And we have mu of x equals mu, sigma of x is sigma over square root of n. So we want the probability of x bar, okay, find the probability of getting a mean of 98.2 or less. Okay, so we want really this one. So we want to start with this one. We want the probability of x bar being less than or equal to 98.2. If you look at the graph with the given information, this is how it looks like, but I'd rather look at the graph when we are dealing with the z-score. And so we have to go from x bar to the z-score. By the way, this is a continuous random variable, which means probability of x bar less than or equal to 98.2 or probability of x bar less than 98.2 makes no difference for this is the same as probability of x bar less than 98.2. Why is that? Because it's the continuous random variable. For a continuous random variable, probability of a single value is 0, which is not the case for a discrete. So it really makes no difference in any event. So now we have the mu. We calculated the sigma of x bar. So let's calculate the z value. So 98.2 minus 98.6 over 0.62 divided by 106. We've already calculated it, and it becomes negative 6.64. I would graph this one, and so I'm interested in this. So take a look at the bottom of that shape. I'm showing you x bar of 98.2 corresponds to a z of negative 6.64. Looking up the table results in almost nothing, 0.0001. Whether you use a table or technology, that is absolutely fine. So what does it mean? So assuming the population has a mean of 98.6, that's what the common belief is. We have a sample size of 106 that is randomly selected, and the key is randomly. Randomly is important because it gives you the proper result. You want to find the probability of getting mean of 98.2 degrees or lower, and that is very small. So let's see the interpretation of that.
The result shows that if the mean of our body temperatures is really 98.6 Fahrenheit, as we assumed, then there is an extremely small probability of getting a sample mean of 98.2 Fahrenheit or lower. 106 subjects are randomly selected. University of Maryland researchers did obtain such a sample mean, and after confirming that the sample is sound, there are two feasible explanations.
What's the first one?
The population mean really is 98.6 degrees Fahrenheit, and their sample represents a chance event that is extremely rare.
What about the second one?
Population mean is actually lower than the assumed value of 98.6 Fahrenheit, and so their sample is typical. Because the probability is so low, it is more reasonable to conclude that the population mean is lower than 98.6 degrees Fahrenheit. In reality, it appears that the true mean body temperature is closer to 98.2 degrees Fahrenheit.
If we go through the process, then the process perhaps tells us that the common belief of 98.6 may not be true. Of course, this either happened by chance, which is very rare, or 98.6 is out. And so you can try this more and more and come to a better belief if need be. So I think recently they have come to the realization that 98.6 is not a population. Here's the next one.
Assume that 3 children under the age of 6 watch an average of 25 hours of television per week. Also, assume the variable is normally distributed and the standard deviation is 3 hours. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours.
So we are looking at the question. It's a word problem. Let's see what is given as we read the question. So the age doesn't come to a calculation. This is the mean. And we are assuming that the children under the age of 6 watch on average. That means all, that means mu. We are also looking at normal distribution. And the standard deviation, or sigma, is 3. So this is mu, this is sigma, and this is the sample size, n. So the very first thing, what is given? As we read the question, it is a normal distribution. Mu is 25, sigma is 3, n is 20. Because we are dealing with normal distribution, we don't have to worry about anything, any size, n will do the job. So with that being the case, we want what? Find the probability that the mean. So find the probability that the mean. So if probability of x bar is larger than 26.3. So this is what we want to find. And to do that, from x bar, we are going to go to the z. If we look at this just the way it's given, this is what we want. But to go to the z, z is x bar minus mu of x bar over sigma of x bar. Simply put, mu of x bar is the same as mu, and sigma of x bar is sigma over square root of n. So this is the formula we are going to use. Calculate the z score using this formula. Gives us 1.94. So we want the probability of x bar larger than 26.3, or probability of z larger than 1.94. So what I would have done, I would have gone with the z. This would be 0. This would be 1.94, and this would be the region of interest. And so z is larger than 1.94. The fastest way to look up a table, z less than -1 by symmetry. You can look up the z score less than -1.6. This would be the fastest way to read it, I would read this portion. This is z-score of negative 1.94. That is the fastest way. And that's 0.0262. So the probability that the mean of the number of hours they watch will be greater than 26.3 hours is about 2.62%. So let's look at the technology to refresh your memory, okay? Remember what we do? We do normal CDF, second, vars, okay, the variables. Okay, I hope everybody remembers that. Second, and the variables. And then we put the information. What is the lower limit? Okay, 1.94. What is the upper limit? Really, infinity class, infinity. But as I mentioned before, remember from -3 to +3, it covers everything, about 99.7%, based on the empirical rule. Everybody remembers that. It comes really from the normal distribution and the z-table. So if you pick a large number, it will do the job. It doesn't have to be infinity. Even if you put 100, it will do the job. But let's do 1,000. It's just something like that. And mu is 0, sigma is 1. And if you calculate that, it gives you the same number. You could put the lower limit is like -1,000, and the upper limit is -1.94, and it gives you the same answer. When you use the technology, of course, you don't have to worry about that. But if you're using the table, using the area less than -1.94, it's a lot easier for the sake of reading the table. Also, you could do this if we were to use just the numbers that were given and using 26.3 as the lower limit. In other words, dealing with this one. If you want to come up with the answer right here, it is doable. I highly recommend you stick with the Z, but here's how it works. What is the lower limit? 26.3. What is the upper limit? Again, honestly, if you put 1,000 or even 100 words and you put that, but what is the value of mu? The mu remains as 25, not z. Remember, mu of 25 corresponds to the z-score of 0. This is the mu, and this is the mu. Mu of 25 corresponds to the z-score of 0. Now, for the standard normal distribution, what is the value of sigma? It's 1. What is the value of sigma for this case? Sigma is 3 over the square root of 20. And I've shown you that on purpose instead of calculating the number and put it there. You can calculate the number and put it there. In other words, 3 divided by square root of 20 and put the number there with a bunch of decimals to be on this safe side. But I'm showing you that because I want you to see where the number comes from. 3 divided by square root of 20. And that will give you exactly the same answer. But I hope you stick with the z-score. Okay, that's more proper. Here's the next one. So we discussed the question and the technology.
The average age of a vehicle registered in the United States is 8 years, or 96 months. Assume the standard deviation is 16 months. If a random sample of 36 vehicles is selected, find the probability that the mean of their age is between 90 and 100 months.
The average age, that means the mean, is 8 years or 96 months. So that's mu. We are assuming the standard deviation is 16. That's sigma. A random sample of 36 vehicles. N is 36. And it's larger than 30. So the very first thing we write, the given. Mu is 96. Sigma is 16. And N is 36. And it's larger than 30. We can use the CLT. Now, the question is, find the probability that the mean of their age are between these two numbers. So that's what we want. Probability of X bar between those two numbers. So first, we write the given, then we try to tackle the question. Probability of X bar. And it's extremely important you pay attention to that. Do we use X or X bar? It's very simple. Find the probability of the mean. So with that being the case, we have to use the z-score. Z is x bar minus mu over sigma over square root of n. So for x being 90, we calculate the z-score. For x being 100, we calculate the z-score for both cases. So again, this would be the graph, and I would stick with the z as far as graphing, because from the z, you go to the table. So you graph the z-scores, you go to the table, and you look it up. With that being the case, what is the z-score for 90? What is the z-score for 100? So for 90, z is x bar, which is 90, minus mu, which is 96, over sigma, which is 16 over the square root of 36. This 6 really comes up, this fraction, this complex fraction becomes 6 times 90 minus 96 over 16, because you're dealing with a complex fraction. In case I wanted to remind you about what we have learned in basic algebra. So complex fraction becomes a simple fraction. You do the math, you end up with negative 2.25. We do exactly the same thing with the next one, number 100. We go through the process and we end up with 1.5. Therefore, the probability of x bar being between 90 and 100 becomes probability of z between negative 2.25 and 1.5. In other words, I would go with the z-score and change this to negative 2.25 and this one to positive 1.5 and look up the table. And the reason we calculated in this manner, if we go with the table, we look it up all the way to 100 or 1.5 as far as the z-score is concerned. It gives us 0.9332. And then we look it up all the way to 90, in other words, the z-score of negative 2.25, and then we come up with the answer. This would be this number. This area would be this number. It's being subtracted from it. That's why, if we are using the table. And so what is the probability that the mean of their ages between 90 and 100 is 92.1%, okay, or 0.9210. Let's go to the next example.
A person consumes 218.4 pounds of meat per year, on average, with a standard deviation of 25 pounds, and the distribution is approximately normal. Find the probability that a person selected at random consumes less than 224 pounds per year.
It's important to distinguish between A and B. As we read the question, first and foremost, we notice it is normally distributed, or it says approximately normal. And on the average, a person consumes this much. So that's mu. With a standard deviation of 25 pounds, that's sigma. So the first thing first, we are dealing with a normal distribution. We are dealing with a normal distribution. And mu is 218.4 pounds with the sigma of 25 pounds. So in the first case, it's important to know a person is chosen, n equals 1. And we want the probability that a person selected at random consumes less than 224 pounds per year. This is what we want. It's x, not x bar. So we want to distinguish between A and B. Why do we use x here? Why do we use x bar in the next case? It's important to distinguish between the two. There is n equals 1, whereas when n is anything other than 1, you go with x bar. So n equals 1. And now you know what to do. Again, the graph tells you we are interested in finding this. And I rather have a graph with the z. So the very first thing, we use the z-score of x minus mu over sigma, and we calculate this. So we replace the x with 224. Mu and sigma are found in the beginning. We use those, and we end up with 224 minus 218.4 over 25, or 0.22, which means I would have used the z-score of 0.22 and then look up this from the table. So here's the z-score. Looking up the table, results in 58.71% or 0.581. In the next case, we are dealing basically with the same thing, but notice, and this is what is extremely important, n equals 1 in part A. In part B, n is equal to 40. In fact, it's important to know when n equals 1, you use x. When n is not 1, any number larger than 1, you use x bar. So what we want is the probability of x bar larger than 224. I can't really emphasize this enough. This is how we distinguish between the two. And I mentioned that because in the past I've noticed sometimes students have a difficulty realizing which one is which, okay, and why. So pay attention to n. N is 1, probability of x, and is other than 1, x bar. And now you want to calculate the z in the same manner. Z is x bar minus mu of x bar divided by sigma of x bar, or sigma over square root of n. This is again, as far as the graph is concerned, notice what happens. You have a thinner, if you will, graph. Again, you don't have to worry about that too much when you want to look up the z-score. I just want you to see what happens. The reason it's thinner because the sigma is 25, but sigma of x bar is smaller. It's 25 by the square root of n, whatever n might be. In this case is 40, which means we use this formula. We calculate the z-score, and again, I want you to pay attention to sigma versus sigma of x bar, which is smaller. And again, that square root of 40 comes up as far as changing a complex fraction to a simple fraction. This is a complex fraction. Remember, the definition of a complex fraction is a fraction within a fraction. This is the simplest way to define it. So z is 1.42. You change that to 1.42. So if I'm looking up z table, I would have this 1.42, and I look up this, I go to the positive z-score, and I look this up, and it gives you 0.9222. I want to make sure we understand the difference between the two. So with this situation, if we want the probability that a person selected at random consumes less than 224 pounds per year, that would be about 58.71%. But if you have a sample of 40, I find the probability that the sample mean will be less than that, would be 92.22%. So if I were to rewrite this, it becomes square root of 40 times 224 minus 218.4 divided by 20. Correction for a finite population. The formula for standard error of the mean is accurate when the samples are drawn with replacement or are drawn without replacement from a very large or finite population. What you're looking at is called finite population correction factor. I want to quickly explain that to you. You don't have to worry about it too much, but I want to tell you what that means. So,
Formula for standard error of the mean is accurate when the samples are drawn with replacement or are drawn without replacement from a very large or infinite population. A correction factor is necessary for computing the standard error of the mean for samples drawn without replacement from a finite population. When sampling without replacement and the sample size n is greater than 5% of the finite population of size n, that is, n is greater than 0.05 n, adjust the standard deviation of sample means by multiplying it by the finite population correction factor, where n is the population size and n is the sample size. Standard error of the mean must be multiplied by the correction factor to adjust it for large samples taken from a small population.
here's the formula we have. Z is x bar minus mu over sigma of x bar. Sigma of x bar. And what is sigma of x bar? We are going to use sigma over square. So we've seen that not a big. If we happen to have an independent sample, but when it's not, okay, so samples drawn without replacement, remember, without replacement, it is no longer independent. So what's happening here, this won't work. There is a finite population correction factor. That means two things happen. If you recall, when we were discussing this independency, we said when n, take a look at this one, when n is less than 0.05 times n, the sample size is less than 0.05 times the population size, we assume independence. But if it's not, we can't assume that. So there is a correction factor. Again, you don't have to worry about that. What I want you to notice about the correction factor is this. This is the correction factor. If n is larger than n by a huge amount, then this will go to 1. And that's the idea. But if it's not, so if capital N is really, really, really larger than n, then capital N minus n and capital N minus 1 makes no difference. They are almost the same. Their ratio is 1. But if it's not, the ratio is not 1. But we don't have to worry about it. We don't come across that often, or at least we don't worry about it in this course, although there has been a couple of questions in that sense. But I hope you understand that there is such thing as a finite population correction factor. And again, that fraction tends number 1 if capital N is huge. Summary of central limit theorem and the sampling distribution of X bar.
A sampling distribution of sample means is a distribution obtained by using the means computed from random samples of a specific size taken from a population. Sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. The central limit theorem tells us that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. 1. The random variable x has a distribution which may or may not be normal with mean mu and standard deviation sigma. 2. Simple random samples of all size n are selected from the population. The samples are selected so that all possible samples of the same size n have the same chance of being selected. Conclusion. The distribution of sample x bar will, as the sample size increases, approach a normal distribution. 2. The mean of the sample means is the population mean mu x bar is equal to mu. 3. The standard deviation of all sample means, also called the standard error of the mean, is sigma x bar is equal to sigma over the square root of n. 1. For samples of size n greater than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size n becomes larger. 2. If the original population is normally distributed, then for any sample size n, the sample means will be normally distributed, not just the values of n larger than 30. Requirements: population has a normal distribution or n greater than 30.
So here's the synopsis of what we have. The central limit theorem gives us the value for mu of x bar, which is equal to mu, value for sigma of x bar, which is sigma over square root of n. And what happens is that the requirements are very simple. Either the population is normally distributed or n is large. Sometimes we have both cases. So to use this, you have to be aware of what's happening to the population. If the population information is not given, normally the size we need is 30 or larger. Then central limit theorem can be applied.